Peatlands cover about 3% of Earth and contain about 20% of its carbon soil. When decompose, peat releases carbon dioxide into the atmosphere. Peat accounts for roughly 3.5% of carbon dioxide emissions nearly. This is a significant number, taken all about.
Here's an important, short article from Carbom Brief, carbonbrief.org, October 21, 2019. It tells how more threatening carbon dioxide emissions could be on the horizon as European peatlands dry. Europe's carbon-rich peatlands show widespread and concerning drying trends. European peatlands could turn from carbon sinks to sources as a quarter have reached levels of dryness unsurpassed in a record stretching back 2,000 years, according to a new study. This trend of widespread and substantial drying corresponds to recent climate change, both natural and human-caused, but may also be exacerbated by the peatlands being used for agriculture and fuel. It comes as another study estimates that the amount of carbon stored in peatlands across northern regions could be as much as double previous, widely reported estimates. The papers, both published in Nature Geoscience, indicate a need for efforts to conserve peatlands as sites of carbon storage at higher latitudes. Taken together, the findings are a real concern, according to one scientist not involved in the research, given the key role these ecosystems play in the global carbon cycle. Threatened peat. Carbon versus CO2. The terms carbon and CO2 are often used interchangeably, but there is an important difference. Carbon is an element, while CO2 is a compound containing one carbon atom with two oxygen atoms. Read more. Peatlands form when waterlogged conditions slow down plant decomposition, meaning layers of dead plants accumulate over many years as peat. They are a vital component in scientists' understanding of how the planet's land surface emits and takes up carbon. Despite only covering around 3% of the Earth's surface, peatlands contain roughly a fifth of its soil carbon. In Europe, these ecosystems store 5 times more CO2 than forests. However, the existence of many peatlands is under threat, partly thanks to centuries of human exploitation of peat as a fuel source or fertilizer. Damaged peatlands are a significant source of emissions, releasing around 3.5% of global anthropogenic CO2 emissions each year. Dr. Graham Swindles, a University of Leeds researcher and lead author of one of the papers, lays out the various issues facing these ecosystems in Europe and further afield. Cutting, drainage, burning, agriculture, afforestation. All driven by need for peat as a resource or for land use practices not in line with keeping healthy peatlands. Climate warming and drying is also a major factor in tandem with these. While waterlogged peat will continue to store carbon, disturbances resulting from climate fluctuations or humans damaging these ecosystems allow oxygen to enter it, triggering the release of CO2. Many European peatlands have already shown evidence of this transition, as the vegetation they support shifting from peat mosses to grass and shrubs. Drying trend. The first paper, produced by Swindles and a large international group of scientists, was welcomed by University of Leicester wetland ecologist Professor Susan Page as a robust piece of work, and one with some significant implications. It identifies a drying trend across European peatlands, from Scandinavia to the Baltics, that has become particularly pronounced in the last 200 years. Page explains to Carbom Brief. This trend should be of concern given that peatlands deliver a range of beneficial, but often undervalued ecosystem services, including carbon storage and sequestration and, therefore, have an important role to play in climate mitigation. While the results are not merely the result of human interventions, the authors note that European peatlands may now be moving away from natural baselines. The results were most severe for peatlands across Great Britain and Ireland. As there is no long-term hydrological monitoring data available, the scientists use the presence of shells, or tests, from tiny, bog-dwelling amoeba to gauge historic water levels. They analyzed reconstructions of 31 European peatlands, concluding 60% of the sites were drier from 1800 to 2000 than they had been for the last 600 years. Furthermore, 40% of sites were at their driest in 1000 years, and 24% were drier than they had ever been across the entire 2000-year record. While they concluded that this effect mirrored an increasingly dry climate in the region, they also note that human influence in peatlands is likely to have exacerbated the trend. In total, they identified significant damage by people in 42% of the sites and a further 29% suffering from minor damage. However, Swindles notes that they mostly worked on the most intact sites in Europe, so there are many more that have suffered drainage far worse than this. These results could be particularly significant in light of the second paper, which suggests the role played by European peatlands in storing carbon may be even greater than previously imagined. Doubling storage. In their study, Professor Jonathan Nichols and his colleague Professor Dorothy Petit, both at Columbia University in New York, estimate that northern peatlands store approximately 1,055 gigatons, GT, of carbon. They compared this to a previous, widely cited estimate made by Dr. Zickenyu from Lehigh University and his collaborators back in 2010, who arrived at a figure of 547 GT for the same region. Nichols explains their work to Carbom Brief, noting that past analyses did not properly account for undersampled regions, such as Asia and Southern Europe. Peatland carbon, he says, is normally measured using a time history method that involves averaging together the rate at which carbon has accumulated over time at a variety of sites, combined with the area of the peatland to get the total amount of carbon. According to their paper, past attempts that have used this method have been affected by several known sources of sampling bias. Specifically, the pair highlight the assumption that peat accumulation rates over time are the result of the global climate and are, therefore, similar across the northern hemisphere. Nichols explains to Carbom Brief how their method improves on this assumption. The big difference is how I average all the different sites together. Most of the sites that people have measured carbon accumulation rate at are in Northwest Europe and Canada. So you basically bias your calculations towards those places and away from other places. We tried to fix that problem by weighting our averages based on area, instead of arbitrarily based on how many measurements had been made. The researchers used over 4,000 radiocarbon measurements to determine the age of peat from 645 peatland sites. They incorporated previously unused data from the Neotoma Paleoecology database, together with new computer algorithms for estimating the history of peat carbon accumulation and when peatlands were formed. Nichols notes that while their final figure for carbon storage is considerably higher than previous data-driven efforts, modeling studies have already yielded higher figures. If you used an Earth system model to predict how much peat there should be, it's usually more than what we get when we measure, so hopefully this will make it so they are more in line. Potential shortcomings. Carbom Brief talked to a number of scientists who expressed surprise at Nichols and Petit's analysis, given the far larger estimate of carbon storage it yielded. Others raised questions about the methods the pair had used to arrive at their final figure. Yu, who led the team that arrived at the 2010 peatland estimate, tells Carbom Brief that while he is pleased to see such a paper achieving prominence, he is concerned there are major technical shortcomings that have led to this considerable revision. He tells Carbom Brief that while scientists working in this area have long recognized that accounting for regional differences between peatlands is the right way to go, lack of sufficient data has hampered their efforts. In this regard, this new paper has made a potentially important progress and improvement by attempting the calculations of carbon accumulation rates for each of 8 peat regions, with a goal to account for spatial bias. As part of their analysis, the researchers divided northern peatlands into 8 regions, based mainly on political boundaries, that tend to be reported in scientific literature. They also devised 2 other ways of dividing the region up to eliminate any biases. Yu goes on to say that it is unfortunate and perhaps unavoidable that, from what he could tell, Nichols and Petit had to use a single average carbon density value for all sites, despite the known variation across peatlands. He adds that by incorporating previously overlooked data, the authors of the new paper have included sites that would not normally be considered under the category of northern peatlands. Among these are some parts of southern Europe and even a couple in North Africa. Yu says that, in his view, the combination of these two factors has led to an overestimation of the amount of carbon storage provided by northern peat. Responding to this criticism, Nichols tells Carbom Brief that beyond the average carbon density, they also took into account the considerable variation and uncertainty by incorporating a large distribution of values based on 16,000 measurements. As for the wider array of locations, he says this gets right at the point of the paper. We set out to measure carbon in peatlands based on where we know peatlands to exist, not where we assume them to be. In practice, this means including data from unconventional areas, including regions where peatlands are sparse. Overall, he says their methods were designed to produce much wider uncertainties but also a final result that is closer to the real answer than previous attempts. Real concern. The publication of these two papers serves to highlight the importance of peat for scientists' understanding of the climate system, as well as the need to preserve and restore peatlands. Professor Pete Smith, a soils expert at the University of Aberdeen and Intergovernmental Panel on Climate Change author who was not involved in either study, tells Carbom Brief. Taken together, the studies suggest that high-latitude peatlands are acting as a significant carbon sink, as they are growing in area and carbon stock, but, if they are also drying, there is potential that they could turn from net carbon sinks to sources. Given the huge store of carbon in high-latitude peatlands, that is a real concern. He notes that while the Swindells paper suggests drying may not yet be beyond normal peatland drying cycles, the shift away from long-term baselines may be pushing them closer to a threshold whereby peat formation is replaced by peat degradation, which would lead to massive losses of carbon to the atmosphere. Page says a particular concern is that a combination of these perturbations and human activities have a cumulative effect. Swindells and his team write that with European peatlands in a state of transition, there are already measures underway to restore some of them by damming artificial drains and gullies. They note that these actions may be vital in protecting against both human impacts and future global warming. They say these initiatives must take their findings into account. For his part, Nichols says that considering the threats facing peatlands, it is important for scientists to investigate the total volume of peat available across the world, in order to put a number on how much there is to lose. Peatlands are not usually part of global climate models. If we want to make realistic predictions of future climate, peatlands need to be a part of it. Swindells, GTETAL, 2019, Widespread Drying of European Peatlands in Recent Centuries, Nature Geoscience. Nichols, J.E., and Petit, D.M., 2019, Rapid Expansion of Northern Peatlands and Doubled Estimate of Carbon Storage, Nature Geoscience.